is Stoyan Stoichev. And this project kind of got started kind of strangely in the fact that our lab was trying to come up with ways to improve our dynamic range of plasma proteins being measured. And Chris Wu in our lab had always just kind of, because she's a cell biologist, said, let's just start to think about ways which we can capture membrane particles or membrane-bound vesicles. And reading through a bunch of literature, we felt like we could potentially do this using some charge. So we were looking for a quaternary ammonium-based magnetic bead at the time, so I asked her, suggested that she just goes and buys them from the RESA website. I'm not sure if people have ever gone to the RESA website, but you first enter it pops up. There's like a bunch of things pop up and say, do you have any questions? And so when she started typing about this, what she wanted to do, it turned out that this was Stoyan on the other end of that typing, which we have no idea how it worked with the timeline, the time zone differences that he was dealing with at the time. I think he probably doesn't sleep very much, but anyway, the first thing I think he said is, I don't think this will work. But since then, it's actually been a fantastic collaboration. It's been a lot of back and forth between Stoyan and Justin and our lab, and kind of thinking about how to do this. And they definitely has been fun to work with and see the fruits of this method.
Yes, and I'm very glad that Chris persevered beside my thinking that this won't work. I was pretty sure it won't, but it's actually turned out quite well. So yes, hello and good afternoon, fellow Skylinites. Actually, good evening for those of us that just crossed the Atlantic. It's only 7 hours difference, but I'm excited to be here. I've been using Skyline for a long time, but it's the first time I'm a Skyline user presenter. So thank you also for the opportunity to present this work that is largely been driven by Mike, Chris, and the rest of my course lab. So I'm not going to spend a lot of time on this introduction because I think we all know the importance of plasma in terms of a very important source in terms of biomarker discovery, prognosis of disease, and so on. And we also know quite well that there's a big challenge in terms of the wide dynamic range. And so these high abundance proteins on top hiding the interesting things that you want to measure that are potentially secreted from cells that could be a proxy for disease. And so with very much a mass spec hat on, these are probably the 4 strategies that people use when it comes to kind of dealing with this dynamic range. You can deplete, immunodeplete. You can enrich specific targets at a low abundance. You can fractionate. You can combine this with the depletion or enrichment. Or you can use this kind of cool way to compact the dynamic range using protein corona. So these are all valid approaches, and they all have a pros and cons. In my personal opinion, if you want to have a holistic view of plasma and also to answer specific questions, you probably need to have more than one of these tools in your toolbox to be able to deal with this dynamic range. So our approach has been to go after the enrichment angle, and specifically we are going after extracellular vesicles. And these are quite a diverse range of membrane enclosed particles, specifically the exosomes, as well as the microvesicles are thought to play a role in cellular communication, and they carry interesting cargo secreted from cells that could be used as a proxy for health status of the cell. And of course, there are other lipids, the other membrane enclosed particles like the lipid carrying particles, and you want to avoid those because they're also the higher concentration or higher amount than your exosomes and microvesicles, and can contaminate your signal and not give you the right sensitivity. So there's a few different ways you can kind of approach the collection of cellular vesicles. Typically, this is done using centrifugation and ultrafiltration based approaches. You can do it using affinity isolation or specific precipitation. And these work great, but they kind of have more or less the same challenges. You have to use quite a large amount of plasma, typically 500 microliters and often higher than that. It's difficult to scale these in terms of sample numbers. and they can be quite costly. I'm talking specifically about the affinity-based approaches where you have to use some kind of antibody, which can be an expensive component, especially when you're trying to do large-scale studies. And so magnet, the basic principle behind capture of these microvesicles, exosomes, is to use electrostatic interactions between a quaternium ammonium particle, microparticle, magnetic microparticle, and the different types of phospholipids that are found in the membranes of these exosomes and microvesicles. And we also think, but we don't have direct evidence, that the hyperporous nature of the MagReSyn bead, which is kind of illustrated here on the far right, which we've given away some structural integrity, but we are able to get much higher capacity because of penetration within the bead, is helping in capturing these vesicles and kind of keeping them on the bead post the electrostatic interactions initially happening. So probably one of the most neat things about this method is how simple it is to execute. It's really seamless from plasma to mass spectrometer. So you start off with 20 to 50 microliters of plasma. That's plenty to do on any type of mass spectrometry system. You would mix your sample 1-to-1 ratio with this just pH 6.3 with a bit of salt. You add the quaternium ammonium beads, incubate for 30 minutes, and after 3 washes with the same buffer as the bind buffer, you have your purified microvesicles. At this point, you can do salt-based dilution if you want to do non-mass spec-based characterization of these, or you can proceed further. You can just add detergent, SDS to lyse the vesicles. You do standard reduction and alkylation while they're still on the bead. And then the last bit of the protocol is a standard sp3 protein aggregation capture, which is used quite often now in proteomics. Essentially, you would add a high percentage of acetonitrile, fine of 70%. You rebind all the lysed vesicle proteins. You wash your organic, add your trypsin or enzyme, and then get your basically your mass spec ready peptides. So it's really streamlined. It's really slick. You're not changing the bead at any point, so you're keeping the same quaternium ammonium bead throughout, so there's no transfers, minimal sample loss, and it's quite cost effective because you're only using a single bead. I think that's still the most expensive component of this workflow is probably the enzyme that you're using. So because it's so easy to execute the manual format, we can also automate it quite easily. This is already done on a Kingfisher-based platform, so this is a magnetic separator that picks up beads and moves them around to different conditions. So the workflow is split into 2 sections. The first section, you basically capture the vesicle, you remove the abundant proteins from plasma by washing, and then you add your detergent to lyse the vesicles, reduce and alkylate. That's where the first method ends. And then you basically run a second method where you do the standard sp3 pack workflow to kind of capture the proteins, wash them off, and digest them to get them ready for mass spec. So essentially, you can do 96 samples in parallel. There's no centrifugation, filtration, no buffer exchange. And so you go from plasma to mass spec in about 4 hours. That includes your 2-hour digestion for ready to analyze peptides. So what do we see with transmission electron microscopy? We see double lipid enclosed vesicles that are of median size about 150 nanometers. Compared to non-depleted plasma, we see high enrichment of marker proteins for exosomes, microvesicles, as well as apoptotic bodies. And we also see a very high depletion of the high abundant proteins that you typically see in plasma that kind of hides everything that's underneath. So ultimately, this compacts the dynamic range of your sample and allows us to go deeper into the plasma proteome. So with a 90-minute gradient in a orbital fusion with gas phase fractionation DIA, just over 4,500 proteins could be detected. Most of these proteins on the left are the abundant proteins from plasma that are highly depleted, and the highly enriched proteins that we see are functionally enriched for membrane vesicles, extracellular vesicles, and so on. The method is highly reproducible, and also quite linear. I mean, a lot of people talked about the matrix max curved. This was also tested with the same approach, where the sample, the plasma sample, was diluted, serial diluted with equal dynamic range complexity chicken plasma, and we can see that down to about 1 to 20, we're okay. But then once we hit 1 to 100, we start losing our linearity because we're probably below the limit of quantitation at that point. So how does Skyline aid in all of this development? I think the first thing was that the data that Mike and his lab generated and what we were doing validating on our side is generated with completely different platforms. And this is a scenario will happen everywhere. And the beautiful thing about Skyline is that you can integrate or bring in data from different vendors, and you can also bring in data that's processed in different ways. So we prefer to use Skyline. In Mike's lab is Encyclopedia DIA, and then we can bring the same data, and then once you upload it to Panorama and have a common project, we can then view the data and make sure we're looking at the same signals. I think this is a more robust way than just basing your conclusions on protein identifications. And this is just a few screenshots from Panorama, but you can kind of view the layers from all the layers of the, you can view the data from all the layers of the onion, so you can go from the bottom, from the spectra, all the way to kind of the extracted chromatographs, protein groups, and so on. And of course, you can also download the data so you can look at it on the other sides in terms of just within the Skyline environment. Yeah, so I touched on kind of protein identification not being a robust way to measure the performance of the method. So this is the data that we would get in our sites. So obviously the numbers don't look that impressive. You're getting about 1,400 kind of proteins, but we're running a 30-minute gradient, and it's kind of generated on a 10-year-old plus 5,600 system. So yeah, the struggle is real, guys, and we are going to have a collection box at the back. So just drop your collections for a new mass spec. But you know, this is the reality of the situation. And if you look at it just from a numbers perspective, you think this method is not working, but you're still getting 5 times the number of proteins of what we see in the undepleted plasma on our system. And I think more importantly, what you're seeing is that the same high abundance plasma proteins are being depleted, and the same vesicle proteins are being enriched. And so therefore, for us at least, the method is working. And so what we want to try and do is, you know, in terms of kind of monitoring method performance and also beads reproducibility when you're producing these things, we want to have a functional assay and want to have stay away from protein identification as a metric and basically look at it in a more targeted way. And of course, Skyline is really good at that kind of thing. So what we've done, and we've looked at the methods, and we decided that there's kind of two portions to it. There's the front end capture / depletion, and there's the back end digestion. And so we were thinking about how do we actually monitor this in a more targeted way. And so the back end, that's already something that's established. And so we would monitor it by spiking something like enolase, and then you can look at how this protein is performing. You can see that the digestion efficiency and so on is reproducible. The front end is a little bit more tricky, but so we thought about using something like commercially available vesicles. They can spike in plasma that's depleted from vesicles. That's quite an expensive way of doing it. So we thought, what if we just monitor the relative enrichment and depletion of these things that we are monitoring, so we can have report the proteins for proteins that are going down and proteins that are going up typically. And so we started to design this targeted assay of about 60 proteins that can give us this information. And kind of the example I want to illustrate this is when we compared in a very small study fresh versus 6-month-old plasma to see if that is kind of working still okay. And so the data is still required with DI, with SWAT, but it's kind of viewed in a more targeted environment. So on a high level or on a satellite level, as Brendan will say, we can see that there's a very little correlation between undepleted plasma and the vesicle-enriched plasma, and there's very high correlation between the two types of plasma, old and fresh. So this is okay. What happens if you go a little bit deeper into the data? So we look at our inlays, and we can see that intra-batch and inter-batch, the signal for the 7 or 8 monitored peptides is really stable. So in order that our recovery has been good. And we also see that the coefficients of variance within batch and across batches is also quite stable. Most of the peptides are below 15% of CD. So this gives us the confidence that the back end of the method is being stable and it's been reproducible. What about the front end ability to enrich and deplete? So now we start looking at specific reporter proteins that are giving us this information. So here I'm showing albumin, which is one of the highest abundance proteins in plasma, versus CD, I think 44 or CD40. And this is one of those peptides that we're monitoring. And in Skyline, you can see this very beautifully how the dynamic range is being compacted. So this is pre kind of enrichment, and this is post-enrichment, and you can see that between the two types of plasma, there's hardly any difference for this particular peptides. If you also notice that we've kept a lot of these cysteine and methionine containing peptides, and our thinking is that we can also use it in the future to monitor the alkylation efficiency as well as the age of plasma by looking at oxidation levels. So you want to have those as like in the back pocket to kind of enhance the assay as we go forward. And of course, within Skyline, you can do these group comparisons and plot these bar charts. And then you can look at all these 60 target proteins and how they're changing between the two different types of plasma. And if you actually overlay them, you can see that you have a very high correlation. And that gives you the confidence that fresh versus 6 months plasma is actually working okay in this scenario without even going to look at any number of identifications that's been acquired. You can always layer this later, but I think this is a more robust way of looking at the method's performance. And just to end, another tool that we've been using quite a lot to kind of understand if the method is working is the use of the tool PROTTER, which you can install via the external tools. And then once you install it, you'll get this report available in the reports section of Skyline. And then you can export all the proteins and peptides that are found in the Skyline experiment. And then this goes directly into the Prot server. And then for each protein that you've identified, to match the peptides that are identified. This is shown in blue. And then it also identifies if there's any transmembrane domains. And so based on this type of analysis, we estimate that about 40% of the proteins detected have transmembrane domains. So I think Magnet is kind of a new tool that hopefully you guys want to try out. It's, I think, really geared towards high throughput profiling of plasma. It's efficient in compacting the dynamic range. It requires a low input of material. It's high throughput and it's quite cost effective. And I think also Skyline is really be helpful in this ability to bring in data from different environments, but view it on the same platform to make sure that actually we are looking at the same signals. PROTTER, as I said, to look at transmembrane topology. I didn't talk about this bit here, but we've used Skyline quite a lot to do group comparisons and to understand the mechanism of action. So there's been quite a lot of work in terms of which types of beads are the best to work. And I think we're probably just starting to look at the possibility with this method because we can see that using different functionalities, we can select the different types of vesicles. And so I think this is something that's going to come going forward as we can actually improve the selectivity of this method even further. And of course, the targeted-based analysis that is enabled in this Skyline is something that's been really useful to monitor method performance. So this is it in a nutshell. I want to thank the team from Across Lab. It's been a wonderful collaboration. It's been really open and fantastic. The team from Resin Bio and CSRR, and the rest of you for your time. And if you want to see a little bit more about Magnet, there's a couple of presentations, there's a poster, and you can see us at booth 709. Thank you.
was curious if you tried this retro approach on other fluids, like cerebral spinal fluids, saliva.
So we haven't, but in my lab they've done CSF, and it does work with CSF quite well. And we want to try it also with urine. We're not sure how it's going to work with electrostatic interaction, and urine's got a lot of salt, but so does CSF. And it seems to work quite well. We need to use a little bit more material than what's shown here for plasma, but it's, yes.
And also CSF, the concentration of the vesicles is like 1/10 to 1/20. They found that should be like 10 times to 20 times more CSF, which is even harder to get. So it does work. We've done more quantum microwaves of CSF.
So, quick that's stuff. Are these available? Can you buy them?
So these actually, so there's a lot of work done by Mike and Chris by testing different beads, but it turned out that standard sex beads that we had actually work the best as they are. And so yes, they are available.
It's just the off the shelf from the anion exchange.
So, do you have a protocol published, or is it just
We have it. I think it was just put up this morning on bioarchives as part of the Astro.
There'll be a more detailed one that goes up by this week. So.
great? Okay.